Here's the last screencast for Lab 1. We're going to split up the parts that I had before into more mini parts. So we'll talk about a voltage divider. That's very important. There's going to be so many things that we're going to turn into the equivalent of a divider. The voltage divider actually also gives us our concept of source and load impedance and input and output impedance for that matter. And that's going to go throughout the whole course, at least at analog circuits. And then we'll talk about the Thevenin model, Thevenin equivalent circuits, and a little bit about Norton. So in this class, we're going to turn almost every complicated circuit into one that looks like this below. And this is a new notation. Right here, this is the voltage divider. And what we're going to find out is the voltage at V out is some fraction of the voltage at V in, and that's going to depend on the resistors. And let me give them a label, actually. For now, we'll call them R1 and R2. And you're going to see this circuit over and over again, and R1 and R2 are going to be given particular names, as you'll see. All right, just for this new look here, look, these points, these are both ground. We could draw a line and connect this together, but we're kind of done with that. We're not going to draw batteries so much anymore. We're going to think of circuits as having two inputs and two outputs. Here's the input, V in and ground, and here's the output, V out and ground. And this is a more signal processing type of analysis. So in fact, we could draw the circuit if we didn't know what was inside. And now what I'm drawing on the right here is any circuit at all where you have two outputs and two inputs. And in fact, by knowing some simple things like input and output impedance, we often hook up things that are black boxes. We don't quite know how they work, but we know a little bit about what their inputs and outputs will do. So this would be like V in over here, and this would be V out over here. Okay. And in fact, my claim is any circuit you can basically model like that, and then you hook up more of these black boxes. And if you have some idea about input and output impedance and some of the functionality, you don't need to know necessarily what goes on inside. But now let's talk about this voltage divider here. Okay. So again, here's V in. And V out, you're taking at this corner here. Okay, so here's our voltage divider up in the left-hand corner, and the question we're interested in is what is V out in terms of V in? That's often what we want to know. We put a signal into a circuit, and how does it come out? All right, and often we know what we put in, and we measure what we put out, and if we can find the relation between it, we can tell what the circuit does. All right, and so what we'll find soon after we move off of DC circuits is these components here can be more interesting. They can change with frequency, and they can make filters and all kinds of other interesting circuits. So the first step is let's find some current in this circuit. Again, what we want to find is we want to find some relationship between V out and V in. And so the first thing we're going to do is let's just find I. All right, so this is I, and that's I as well. So there's no junction. Even though I've drawn the circuit like this, and I want you to start getting used to the way this looks, remember, these lines are connected. There's no junction. These are two resistors in series. What makes it just maybe different is we're interested at the corner here between the resistor, what the voltage is. All right. So I is the same through this whole circuit, and so therefore we can write I. Oh, let me choose a different color here. So I is just going to be equal to V in. I'm going to say I'll just write it out minus 0. All right, that's the entire voltage drop here. Right, is V in to 0 divided by R1 plus R2. Right, the whole effective resistance of this thing is R1 plus R2. Okay, so I is just going to be equal to V in over R1 plus R2. Okay, let me make that just a little smaller, maybe move it out of the way a bit. Okay, just so it doesn't get too close to the circuit. Let's that's great. Now let's see if we can find something related to V out now. All right, V out and I. So V out, again, it's the same current through the whole circuit, is just going to be I times R2. Okay, and so if all we need to do now is we need to plug this current into here, and we have V out in terms of Vn. And so maybe you see it already. When we combine these two equations together, we get V out is equal to V in times R2 over R1 plus R2. Let me make that plus a little bit neater there. Okay, there we go. Pretty simple, all right. But there's some amazing things that happen with this. Let's look at let's just look at what happens when. Let's just take some cases. So how about what happens when R1 equals R2? Well, can you see when R1 equals R2, we would get 2R2 on the bottom and 1R2 on top, so that'd be 1/2. So when R1 equals R2, V out is going to be 1/2 V in. Interesting, okay? So that makes sense, right? We've did some of this in the concept. When the resistors are equal, the first one drops half the volt, and the next one drops the other half. So if we're looking in between them, we're going to get half out. All right, how about a more extreme case? What happens when R2 is much, much less than R1? Okay, so let's look at that. How it happens when R2, okay, R2 is much, much less than R1. What's going to happen then is basically this is going to go to 0. That would be going headed towards a short. So we would say V out goes to 0. All right, because basically you can think about it as this resistor here gets tinier and tinier and tinier, it's going to start drawing a lot of current, and these 2 points are going to be the same, right? The ground is going to be the same, so that'll go to 0. Let's look at another case, and that would be R2 much, much bigger than R1. All right, in this case, if R2 is much, much bigger than R1, we can basically neglect R1. R2 much, much bigger than R1 is negligible compared to R2, and V out equals V in. Okay, so we have basically there's the 2 and 3 are the limiting behavior. As R2 gets very, very tiny, you're basically basically R2 becomes a wire. The V out's going to be 0. All right, so you basically shorted out part of the circuit, and you're going to be drawing a lot of current. On the other hand, if R2 is very, very big, then you get out what you put in. You might be able to see where this is handy. Okay, so this is just a similar picture of the voltage divider we had before. I put it inside a box, and this is often a common situation we have when we're hooking 2 circuits together. So our load can actually be an entire circuit, and we're representing it just by this resistor. And this complicated circuit, it could be a complicated circuit, and we represent it just as a source and a source resistance. Okay, so basically these both could be 2 very complicated circuits, and we're representing one by a source and a resistor, and one with just a load resistor. And when we put them together, we get a voltage divider. And so you can imagine this, a simple case might be this is a function generator. And the function generator has some internal source voltage, but there's some source impedance. And we want to know what happens when we connect our circuit to the function generator. How much voltage will be delivered to this load RL. So L is for load, S is for source. We can also call this source impedance here, we can also call it the output impedance, because it's what we would see when we're looking into the device backwards into its outputs. So our source is the output impedance. This is our equation we had. It's just instead of R2, it's RL, and instead of R1, it's RS. And let's actually make a graph. This graph is a little more complicated than it seems. It's just a line, but there's three variables basically going on here, or at least one that's not totally independent. So let's draw an axis here. And here's what I want to show you. I want to show you V out versus I. All right, and let's talk about actually what those mean. So V out would be after I connect the load. That's the V right there. All right, and the I is going to be the I through the load. So I guess I should let's call this I load here. So V out and I load. All right, and now here's V out, the equation here in terms of RL. But how about in terms of I load? Well, we have that equation too, and that's just going to be, we know that V out is just simply going to be I times R load. All right, but we have to be careful because I is going to change with R load as well. So I guess I should say load and load here too. I load is going to be equal to Vs RL plus RS. Okay, basically from all these equations what we're going to get is that what we're interested in here on this graph is what happens to the V out versus IL as what happens to the current going through here and the voltage on here as I change the load values. Okay, so pretend now I have a whole bunch of different, I can change this to 10 ohms, to 100 ohms, to 1 mega ohm. I'm going to see what happens on this plot here. It turns out we get a line. See if I can draw a straight line here, almost. Let's try that again. A little better. I'm going to circle these points on the axes because these are important points here. Try to make that one a little darker there. Okay. So basically, if you remember from the last slide, what happens, when is the case, well, I guess we should put a value here. When there's no current going through this resistor here, when there's no current going through this resistor, what would the voltage be here? When there's no current going through this resistor, that's as if that resistor is super, super, super fat. All right, like very, very, very large value. So when there's no current IL, that's this point here, the y-intercept, that would be for RL equal to infinity. That's an open circuit. And that's going to have the value of V out there is going to be Vs. Okay, let's go to the other case, the other extreme. How about down here? This is the maximum value of I load. When do we get the maximum current through here? Well, it's when we short it out. It's when RL equals 0. So this is for RL equals 0. And so we can label this as I short. All right, this is Vs actually here. This is V open. Okay, maybe we should label it a third way too. Although it's getting crowded, we won't. So Vs here, we know that that's the open, right? This was one of our light bulb questions too. Look, when nothing's connected here, the voltage at the end of the resistor is the voltage here. So this is the open voltage, and this is the short voltage. Let's label those in a different color just to make it. So this I short, actually, I'm actually going to put it here. This is V open. And the I short here is going to be equal to, it's just when RL equals 0. Okay, and so when RL equals 0, down here, RL equals 0, we just get Vs over Rs. Okay, so I short is basically Vs over Rs. Okay? That's helpful because we can actually get the slope of the line just from these 2 points here. All right, if you're following me, I know it's a little bit messy. This point here is Vs. It's also V open. This point down here is I short. It's also Vs over Rs. All right, so the slope of this line, which is going to be an interesting thing we'll see, the slope of the line is just going to be equal to, this point here is going to be V open, right? So rise over run, this is going to be, here we'll do this compared to this point over here. We'll have Vs minus 0 over 0 minus I short. Okay, let's see. Can I move that one around without moving too much? Yes. All right, let's... and actually, let's box some of this off over here. Just because we're getting a little crowded here. Okay, and then let's take this slope here, and you might already say that that's just going to be equal to Vs over minus Vs over Rs, which is going to be equal to Rs. All right, that's getting a little bit messy too. Let me box that. And then let's look at this kind of complicated curve. It's just a line, but there's a lot going on. So here's what's going on here. We are pretending now that we're putting different loads onto here. And as we put different loads, we're drawing different amounts of current through here, which is giving us a different V out. All right. So imagine you're putting many different. We put a short on, and we draw all Vs over Rs. All right, and that's our. But we have 0 volts, so we draw a lot of current, and all that current gives us 0 volts. And we go up the curve where we're halfway, where we put on a RL that's equal to RS, and we get half of Vs. And we keep going up, and then when we have an infinite amount, it's like it's an open circuit, right? If I have a resistor so big that I put on here, it's as if it's open. All right, so here's the extremes. Open is here, short is here, and these are all different values of RL. For every different value of RL I put in, I draw a different amount of current, which is corresponds to a different V out. All right, we'll talk about how this is helpful for Thevenin equivalent. This is where all of the theory on source impedance and output impedance is going to pay off. So if you look, this is just another version of our circuit we had. Now I'm calling it TH for Thevenin. So basically, any complicated mess has a Thevenin equivalent. Let's write that down. Thevenin equivalent. Okay, and then the graphical method that we had just on the other slide is the way to find the Thevenin equivalent. So in real life, if you wanted to find the Thevenin equivalent of the circuit, you could rewrite it to actually just model it like this. What you would want to do is you would want to put on many different R loads onto this, and you'd measure the voltage drop across that load and the current through it. That was our chart before. So we had our graph we're interested in V out and IL, and that would be as you added. So let's add a little load here. Let me. All right, so that one's not connected yet. That would be an RL. So as I pop on different RLs onto this, what I'll get is I'll get a graph, that line, and the slope of the line is equal to R Thevenin. Okay, and that's what we need in our circuit. And then the Thevenin voltage is just the open circuit voltage. All right, remember V open was here. That's the open circuit voltage. And so you can get the Thevenin equivalent circuit by just taking a multimeter and measuring at the output. And then you can get the R Thevenin by putting on many different loads, measuring the current through the load, the voltage out, and the slope of that graph. That's what you're going to do in your lab. Now there's a quick and dirty way to do it. You could actually just get it from 2 points if you remember, but this is not a great thing to do in a real life circuit. So remember that our Thevenin, we had it called RS before, is going to be V open over I short. rather negative. That's the slope. All right, so R Thevenin is positive, but the slope of the line is V open over I short. This one down here, this was I short. So you can get the slope from 2 points by measuring the open voltage. This would be the open up here, and the short. So if you shorted it and measured the current through it, you could get I short. And then if you measured open, you get V open, and then you get R Thevenin in 1 point. The only thing is you just destroyed your circuit by doing it. So in lab, rather than destroy your circuit and run lots of current through it, you're just going to get a handful of points on this line, and you won't short it. You get the open, that one's safe. Put a multimeter, there's no current flowing through. But then you'll draw more and more current through, but not so much to short it out. And so then any complicated circuit, let's can be it has a Thevenin equivalent, and here's the Thevenin equivalent right here. Very, 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 very handy. What you'll do for your homework is you'll have a nasty circuit like this, and you'll do that same procedure, but you use the simulation tools to do it. In this case, in simulation, if you short it out, that's fine. You won't hurt the virtual circuit. You won't smoke the virtual circuit. For simple circuits, you don't need to use the graphical method to find out. You don't need to be in lab or have a simulation. So what we can do, this is not a very complicated circuit, so it's a simple one. And so if we want to find the Thevenin equivalent of this circuit, which is a voltage supply with resistor A and resistor B, here's where V out is. All we simply need to do is short the power supply. That means turn that into a line. These are connected anyway. So here's what I have, and now it looks like a 200 problem. As you can see, I'm looking at the point here where current would split and come back together, so it's basically parallel. If I'm looking at these 2 points and calculating the resistance of RA and RB, because I'm looking here, it looks as if the resistance is in parallel, and that's the Thevenin resistance. Let's talk about Norton real quickly. So to explain a little more what Norton equivalent circuit is, let's go back to, or not go back, but give you a definition of Thevenin's theorem. So Thevenin's theorem says that any linear circuit can be replaced by a single voltage source and a resistor in series with that source. That's what we were just seeing here. Is you can take a big complicated mess, could be a bunch of components, power supplies, and we can recreate the circuit as if it were just one source and one resistor in series. The Norton equivalent of that is that you could take a complicated mess, maybe that same complicated mess, and treat it as one current source with one resistor in parallel. So typically, just like in E&M, we like to think of, or many people like to think of electric field in EM waves rather than magnetic field, even though there's one there. Often in electronics, we tend to look at things from a voltage source perspective. Not always, though. So in this class, we'll be mainly concentrating on the voltage perspective. But there is this current analog, which has this opposite effect. Series goes to parallel, voltage goes to current. You can often just flip a lot of these rules, and it'll work for Norton. As a final note on Thevenin and Norton equivalent, this relates in general to voltage sources and current sources. What makes an ideal voltage and current source? So voltage sources keep V constant despite heavy loading. Heavy loading for a voltage source means that RL is small. If RL is small, it draws a lot of current and it pulls down the voltage, so the voltage here is low. So you don't want that, so RL is either big. Another way to do that is you make RS small. If RS is small, if your output impedance is small, that's going to be a good voltage source. It's opposite for current sources. In order to keep the current constant through the load, or the current as much generated through the load, you want to have very small loading. You actually want this small, so therefore all the current goes through this rather than your source impedance. So basically you want RS to be big, you want your output impedance to be big, so that most of the current goes through RL. All right, and again, let's go back here. Here you want RS to be small so that most of the voltage gets delivered to your load. So a good voltage source delivers all the voltage that you have at the beginning. V out equals V in. If RL is big. A good current source delivers all current to RL. That works if RL is small, or rather RS is big. Wow, that's a lot of stuff. Hopefully this will be helpful for lab, and we'll be talking in detail together.